waiting room, as long as they're not the robots, we're good today. So with that, I want to introduce our keynote presentation and speaker, Everett Phillips. Just delighted to have Everett with us today for many reasons, not only his intellect and his industry knowledge, but because it turns out Everett is one of the co-founders of the original CTBN. CTBN originated in Orange County, California, as a group of alumni interested in networking professionally in a brown bag lunch event. It happened during just before COVID occurred, after about 3 or 4 events, if I recall. The university shut everything down in person, including the original brown bag CTBN. Things grew from there. A few of us connected across geographies. We said, why don't we take this thing virtual, national, all colleges, not just engineering and business. And that's what we have today with CTBN. So here's the one of the masterminds for the initiative of what we have today. So we're delighted to have Everett for that single reason. But beyond that, as you can tell, Everett has his bioengineering degree from Cornell in '82. He was a member of the Quill and Dagger Society. He earned his MBA at UCLA Anderson in '90. He's been very active with Cornell on the advisory board for entrepreneurship at Cornell, a board member of the Cornell Club of Orange County, University Council at Cornell, also a board member of the Cornell Engineering Alumni Association. And he's also, besides Cornell, a board member of the UCLA Alumni Association. Professionally, Everett is a consummate entrepreneur, and I would say one who likes to tinker with technology. That may be an understatement, Everett, I apologize, but from days back at Seiko Instruments in a division factory role to general manager to responsible for management information systems, business development, ERP, BI, all of the uses of the technology, to becoming president and CEO of a China manufacturing network, co-founder and director of business development for P&Q Technologies, and on and on. More recently, with his work at Lyric Robotics, and then after that, as a consultant coach at A2BW, Everett now is considering himself a consultant and the roboticist, focusing on exponential technologies and the convergence between those technologies. Everett, I'm going to leave it to you to fill in the rest of the gaps. Quite a story. Glad to have you here. And I'll tell you what, we're going to shift gears on slides. If you are ready to take on the helm, we'll shift your machine.
Can you see the slide?
Yes.
Okay. So I'm really honored to be able to share 40 years of experience in robotics with you today. So I started with programming my first robot in 1982, wrote manuals on how to program, wrote service manuals, how to take robots apart, put them together, was involved in applications of robots. Eventually became the general manager of the startup that I was part of, ran operations in Europe, ran operations in North America, sold it to Seiko Epson, and then started another company related to manufacturing and automation related to China. So there's a lot to cover, but let me just, what we're going to go over today is really a little bit about what is a robot, why industrial robots have transitioned into all these other areas, what are cobots and exoskeletons, and this convergence of AI and robotics, and then the outcome of that convergence, and this new humanoid robot that you're constantly seeing information about. So to start off, we have to just discuss mechatronics, because mechatronics and robotics are related to one another. Mechatronics is the superset. It was a coin started, the term was from the 1960s, from Yaskawa. It's really this convergence of mechanical engineering, electrical engineering, computer science, control systems. It involves everything from CNC machines to any device that's using these different technologies. So while all apples are fruit, not all fruit are apples. And this is where robotics come in, because there's a lot of confusion between robotics and mechatronics. But there's no single unified definition of robotics. This is a problem if you want to tax them, or if you want to have tariffs on them, or if you want to have, because there are a lot of mechanisms that for marketing purposes people call robots but aren't really robots. So the term robot came from a play in the 1920s, a Czech play where it was about these automated pieces of equipment. Robota is a Czech word meaning forced labor or servitude or drudgery. Today, we kind of look at robotics as having key characteristics of a physical embodiment. So not the software robots you hear about running around the web. Programmability, it could be doing a bunch of different tasks. It has sensing and manipulation capabilities and autonomous operation to some degree. Now, one type of robot that actually has a definition is an industrial robot. The industrial robot is automatically controlled, reprogrammable multi-purpose manipulator, programmable in 3 or more axes. It can be fixed or it can be moving. There are many different kinds of industrial robots. So they're articulated, they're SCARA, they're Delta, they're Cartesian. It's not necessary to go into all of them, but just so as we talk about the term industrial robot, you have an idea of some of these different looks. There are even dual-armed robots where 2 arms are working together. It's kind of fascinating to see them working together. This is not artificial intelligence. This is regular programming using a CPU, nothing, I mean, it's special, but I mean, not AI special, right? So I really want you to understand that robotics has advanced a lot in capabilities without AI. The robots started in the 1960s. In the 70s, they started to become more available, but really it's the late 70s, early 80s where they started to really take off. In my opinion, you had Fanuc, Yaskawa, Kuka, ABB, people who made CNC machines, controllers, things like that, had an advantage, and they've grown common robot people today. Then there were large internal users like Toshiba, Seiko Epson, Denso, Kawasaki. These people needed equipment internally, so they developed a robot to use internally, maybe hundreds or thousands of them, and then sold them to the outside market. So that made entrepreneurs struggle. So in the early days, there were robots like Puma, Merlin, and then recently Rethink. They died because they didn't have enough internal skills or capabilities, enough volume to be able to compete with people who were really just selling excess. Adept is a company that did very well in the 80s, 90s, and early 2000s, but was eventually taken over by Omron. In 2012, Amazon bought a robot company called Kiva, used it internally. Today, now 750,000 of those robots are in use in Amazon factories. So where does that place us as far as robots worldwide, right? There are 517,000, robots sold in 2021, which is the last year I have data with, but you can see the trend over the prior decade. That means there are about 3.5 million robots operating in facilities at this time, right? When we say robot, right, industrial robots, there are cages around them usually. There are sensors. There are things that prevent people from interacting with robots. This has been really the trend for 30, 40 years. In the last decade, there's been the evolution of something called a cobot or collaborative robot. They're similar to industrial robots, but they've been adapted so that they don't hurt you as much, right? I mean, they still can be dangerous, right? You know, it's interesting that we're putting them next to people because you wouldn't allow a coworker to punch or hurt their coworker and not go to HR. But you have these robots that physically can bump and hurt, bruise. They won't kill. And part of the reason they move more slowly and they have lighter payloads, like 10 kilograms, 12 kilograms. But when you get up to 50 kilograms, that momentum alone can hurt someone. So you have to do a safety evaluation before you can allow the robot to be just working next to somebody. So one of one way is to allow the robots to be outside and inside different containers, right? So this robot's in a barrier, it's a cobot, but outside of the barrier, there are other cobots that are interacting with people, moving around. Those robots move a little slower, but this is a new trend, this cobot. How much of a trend? Well, in the 517,000 robots that was sold, currently 39,000 of those in that year were cobots. So it's growing year by year. Teledyne bought Universal Robotics because Universal has a lot of this technology. So it's something you're going to see and hear a lot more of. Exoskeletons that you hear people talking about are kind of a cobot that you get inside of. One can argue that actually the Tesla on auto drive is a cobot that you sit inside of. Of the 570,000 robots, just to give you a feeling of where they distribute around the world, right? So they're roughly half are sold in China, half are sold in the rest of the world. That's been the trend up until it's now catching up even, but even earlier in the decade, China bought more robots than the rest of the world, which people find unusual because labor is so cheap in China. But robots bring quality, robots bring scalability, robots bring a bunch of other values other than simply replacing people. If you look at the other half, so you have China, 268,000, then you have Japan, the United States, South Korea, and Germany consumed all the rest, almost equal to one another. But if you look at the density of robots, if you look at then the Republic of South Korea is a much larger portion of robots per worker, right? Then comes Singapore, then comes China, then comes Germany, then comes Japan. You see the trend is industrial countries with a small population need a lot of robots per person, and countries that have high labor rates need a lot of robots per person. By industry, robots are divided into automotive, electronics, food, metal, machinery. Automotive is very heavily the big robots that move heavy things around. Electronics tend to be the smaller robots that move things around. The technologies related to robots that are important to understand, at least for discussion now, are inverse kinematics. This is the mathematics behind getting a mechanism to go to a specific spot in space. Spatial computing, which is ability to assign data to three-dimensional space and then operate in that space. And then digital twins, which is a simulation virtual version of a machine that behaves like the machine. So you can actually write programs on the virtual version of the machine and then just download them and run the actual machine. But robots without AI can still do fantastic things. Like here's an example of a robot with vision. This is a Delta style robot. It's moving from above. It's using vision to pick off a moving conveyor, objects, pancakes in this case, and then place the pancakes into rows of 3. So what's going on with AI and robotics merging together? This is called convergence. Convergence leads to exponential technologies. Why? What's happening is costs are being reduced and capabilities increased, which then allows the technology to be deployed into multiple new industries and uses. The problem for business people and investors is that we are very linear thinkers. What we do is look at 10% increases, 30% increases. We can deal with that year to year. We know how to inventory for those things. But exponential growth is something that we as humans have difficulty dealing with. That's one of the reasons why we have trouble with diseases. They grow so fast because they grow exponentially. And we caught unawares because we don't know how to deal with exponential growth of anything. But this creates opportunities because that means that current players cannot foresee a need, and that creates a gap. That gap allows opportunities for investors and for others to get involved with. So these are a variety of technologies that are identified as exponential. Deloitte has a great paper on this. I'll put it on the link in our group. But of it today, it's the advancement in robotics and 3D printing, which is really robots with special dispensers. What's making this happen is the advancement of what's called a GPU. The CPU has been part of a computer from forever. And then a GPU, we have always had in a computer kind of around the graphics, right? So as you had sophisticated games on computers, and if you had ways of pretty pictures, all these things required additional processing capabilities to make your screen look pretty. So it's not a CPU, right, where like that you normally have logic with. So a CPU does math and has binary code. A GPU is doing more calculus, right? So if you look at just comparing the two, a CPU is a foundation in binary. It's addition, subtraction, multiplication. It has logic and control. But a GPU is highly parallel processing. So it excels where you have a lot of things trying to work together. It focuses on floating point math and calculus and linear algebra in particular. This is why it's useful in blockchain, and this is why it's useful in AI. So in summary, you have a CPU, which is sequential. You have a GPU, which is parallel. The core focus is general purpose. GPUs have this floating math capability. It's very good in vector operations, very good in calculus. But in clarifications, both CPUs and GPUs use binary code. CPUs can do parallel processing. That's what you hear Intel and others talking about, but not massively parallel processing that's needed for AI. And GPUs, although they're called graphical processing units, still, they're not just focused on graphics. So what makes them useful? What is a neural net, right? And I want to take just a couple of minutes to go over a very complex topic, but in just a way to try to help you understand. Basically, there are three components to a neural network. There's an input layer and a bunch of hidden layers, and then there's an output layer, right? And it's this combination, right, that allows a neural net to exist, but it's virtual, right? It's not a real neural net. It's not chip components touching one another. So how does this work, right? So the way it works is that at the input level, you give data, and then there's a bunch of differential equations, a bunch of patterns that develop in all those hidden layers, and then you have an output. So when you do something like to ask an AI is this a cat or not a cat, right? What happens is that these middle layers randomly guess. They just randomly guess, and they'll say cat or not cat, right? And then you tell it, yes, it was right. If it gets right, it looks at those hidden layers and then tries to tune and keep some of those parameters, and then it creates a bunch of randomized guesses around those parameters. Then you give it another picture, cat or not cat. And then if it says not cat, right, if it gets it wrong, then it adjusts one way. If it gets it right, it reinforces what it has. This is so supervised learning is where you tag data and you tell it what it is, but it still has to figure out what about that data actually works in these hidden layers. This is how AI learns. It's not program per se. And when people say like the programming in Python or programming AI, they're not programming the AI. What they're doing is tweaking these hidden layers, right? Like volume controls. It's not really programming in the sense that we're used to. Reinforced learning is where you don't have tag data. It's kind of, you have boundary conditions, but you don't know, you're not telling it what to do. It's learning, right? So one of the things that a good example I find is in these hidden layers, say you have a car that you simulate that goes around the track. The car can go forwards, backwards, right, and left, right? So it only can do certain things. Then it knows the walls are around it by sensors. So you don't tell it, right? It just can't go anymore when it hits a wall. So then it generates 100 different permutations of these inner layers, and the car moves along, and then when it hits a wall, you choose the ones that kind of accidentally go around a wall, you tag it, and then that makes those layers free, the hidden layers. And then it generates 100 new programs, but based around that new proximity. And you keep repeating that and repeating that and repeating that. And eventually you get a car that can go around the track. And the track here, you might not be able to see, but there's one car with a donut. That's the one that was successful from the prior time. And that's the one that was kind of the base of the hidden layers that all the new permutations came out of. So you have these permutations, you choose the best, you have these permutations, you choose the best, you have these permutations, you have the best. And then eventually you have a model that will allow a robot to stand, or a robot to pick out of a bin, or these different, it's not a program per se. And this is one of the challenges when people say, well, you should build in ethics, or you should build in certain capabilities, or you should have a stop button. There's no place to put a stop button. There's no place to put, because it's this organic process, if you will, of the system learning how to do a certain task. One of the things that robots started to first use AI for is bin picking, because it's too hard to program, pick up this, get this, do this, when the objects are mixed up together in a bin and they're different shapes and different sizes. So the robot has to learn over time how to approach certain objects, how to identify certain objects, how to pick those objects up. So bin picking is one of the first AI-based applications being proliferated in factories and robotics. The other areas is happening is mobility. So you have, in logistics, you have now these mobile robots that run around. They can pick up pallets, they can unload trucks, they're in warehouses, they are moving all around on their own, right, with certain set of rules, but they've learned how to play together, right, without bumping into one another, right? I mean, it's amazing to see all these different mechanisms running around with the equivalent of air traffic control guiding them around, right? Each one with their own intelligence, each one knowing what to do. Amazon has 750,000 robots like this. So they're not the robots with arms per se, they're robots that are picking up items from underneath, moving these carts around, distributing them around so that your package can be loaded with the stuff that you want to have when you order on Amazon. Nimble Robotics, Fetch Robotics, Gray Orange, Locust Robotics, Venka, all these different companies are getting involved in this robotic fulfillment system business. It's growing. The future of robotics has future of manufacturing has exoskeletons like the gentleman's wearing, mobile robots that walk around, robots that build things, robots put in glass. But now new markets are coming, like loading and unloading trucks, inside the truck, farming, agriculture. These robots now walk around a field, drive around a field, laser trimming weeds from good product, right? So the robot is able to identify as it goes down what's a strawberry plant or what's a plant that the farmer has planted and what's a weed. And it zaps the weeds with laser. It's a organic way of farming, which what people want. You don't have to use chemicals to get rid of the weeds. There's also robots that actually tend and run whole greenhouses. So this robot fills and waters the different pallets. It picks up pallets and moves it into the central area to be harvested. These are the kinds of things that can be done when AI is merged with robotics. Robots are entering services like medicine. Surgical robots have been around for a while, but AI is adding new skills and capabilities where robots are able to now basically put a suture in a grape. They're that refined in what their capabilities are able to do. They can interact with people, feeding people with disabilities. They can clean, and they can also do maintenance, construction, bricklaying robots. We're expanding into a lot of different areas. How much? It's still small markets. So if you look at from 2020 to 2021, you had only 8,000 new robots placed in agriculture, right? I mean, there were barely any new ones, right? So there was no growth. There are 8,000 robots in agriculture. In hospitality, it almost doubled. In medical robots, it's been going up. So, but we're talking 15,000, 8,000, 50,000 compared to 550,000, right? These are relatively small markets. But this is an entrepreneurship area, an opportunity. And if you look at who has the startups in this area, the United States is really leading, with China second, Germany, then Japan. So robots can do stuff now like being told, pick up a cereal box from the table in one room, bring it to another, and put it down. Bring a pill bottle, go and pick it up and bring it on their bedroom table. These kinds of things are not necessarily being fully deployed in the field yet, but they're can be demonstrated and they're actually happening. What's in the field already is robots, humanoid robots like these that are inside a BMW facility, actually loading and unloading machines. They claim with a 400% speed boost and a 7-time improvement in task success, but with 1,000 placements daily. So humanoid robots actually running in a factory. This is happening now, today. This is a robot Digit. It's being tested in Amazon. But the company Agility, you might have seen this robot was on the cover of Time magazine as one of the inventions of the year. So industrial manufacturing, still a lot of players. But now in warehouse logistics, you have all these other new players. In ground-based delivery and in aerial delivery, you have these new players. In agriculture, you have a bunch of new players also. Food automation, Miso Robotics is here in Pasadena, where I live. They're doing fantastic work started with flipping robots. The robots are in the different stadiums serving food, and they've just come out with a whole new robot system for fast food production. Recycling, there are a bunch of robots systems growing in there. Surgical, that's a growing area of robots that can do different types of surgery. Construction and inspection, robots that can literally build houses, literally lay foundations. And then humanoid players. The proliferation of humanoid players is just utterly fantastic. Different styles, different types. I mean, Boston Dynamics was one of the leaders, and we've seen it evolve over time. But with the combination of neural networks and the training that's available, there's more and more people entering because the barriers to entry are getting smaller. And you can blame NVIDIA because NVIDIA just released hundreds of thousands of hours of training for humanoid robots. And they're very dedicated to being the supplier of the technology of humanoid robots, in addition to LLMs like ChatGPT and stuff like that. So just to finish up, just to introduce you, Cornell is not being left behind in robotics, although I was scared they were. In the 1990s, I had $300,000 in robot arms that I wanted to donate to Cornell. When I was general manager of one of the companies I worked for, and I called Carpenter and they said, no, sorry, no professors interested in robotics at the moment. So I had to donate them somewhere else. But since then, we've been doing a lot of work. I think part of that is we have newer, younger professors who are more entrepreneurial and looking at these different capabilities and are excited about the application of technology. I mean, at the time I graduated, a lot of the teachers were more focused on the theory, and the application of technology was not necessarily where their heart was. But with Stanford growing and competing in the world in the way that it is, with entrepreneurship, It's really changed the way Cornell looks at these things and what we're doing in robotics at Cornell. You can go to robotics.cornell.edu and see some of the things that they're working on. So I think we have just a couple of minutes to